Postgres fixed the same race condition twice. One agent reached for an advisory lock, the other for an atomic update. Both passed every correctness test. So I put 500 concurrent checkouts on each, at the same time, on the same table. Only one of them didn't fall over. Quick recap for anyone new here. 2 videos ago, 3 agents hit the same overselling bug. 2 checkouts, 1 unit of stock, both requests reading before either wrote. Claude Code fixed it with a single atomic update, where stock equals quantity. Last video, Cursor fixed the same bug a different way. Once it could see the database topology, pg_advisory_lock around the whole check then write. Both fixes shipped. Both passed the concurrency test at low volume. Nobody asked what happens at real load, so today I built a load test, pointed it at both fixes, and turned the concurrency dial until something broke. By the end, you'll have the actual throughput numbers at 5 different concurrency levels, the exact moment the advisory lock stops scaling, and the one question that tells you which fix to reach for next time. Here's the setup, and I'm keeping it deliberately boring, because a benchmark is only honest if the only thing changing is the thing you're testing. 1 products row, 50 units of stock, 1 Postgres instance, 1 connection pool sized identically for both runs. 2 versions of the same checkout endpoint, same schema, same driver. The only difference is the 3 lines inside the transaction. Version A, Cursor's fix. Begin. Select pg_advisory_lock, product_ID. Check stock. Update. Commit. Version B, Claude Code's fix. 1 statement. Update product set stock equals stock. 1 where ID equals $1 and stock greater than or equal to $2 returning stock. For the load generator, I wrote a small concurrent runner, spin up, and workers, each firing checkout requests back-to-back for 10 seconds straight, tally successes, failures, and per-request latency at the end. Nothing exotic, no fancy cluster, no cloud load testing service. Just enough real concurrency to stop guessing. Both versions run on the same Postgres instance, same machine, same warm cache, so neither one gets a hardware advantage the other didn't also get. 10 seconds per run because anything shorter is mostly connection setup noise, and I reran each configuration 3 times to make sure I wasn't reporting a lucky sample. First run, the control, 10 concurrent workers, 10 seconds, both versions back-to-back on a cold connection pool. Advisory lock, 481 requests per second, average latency 2 milliseconds. Atomic update, 509 requests per second, also 2 milliseconds. Basically tied, 5% apart, well within noise. At 10 concurrent connections, you genuinely cannot tell these fixes apart. And if I'd stopped the test here, which a lot of reviews do, the honest sounding answer would be, doesn't matter, pick either. That answer is wrong. The only way to find out is to keep turning the dial past the point where it's comfortable to stop. Concurrency to 50 workers. Atomic update, 2,100 requests per second, latency creeping to 11 milliseconds. Advisory lock, 340 requests per second, latency jumping to 61 milliseconds. 6 times slower, and the gap is now visible without squinting at a log file. Concurrency to 100, the bridge point. Atomic update, 2,200 requests per second, latency 15 milliseconds. It's already found its ceiling and is just holding there. Advisory lock, 161 requests per second, latency 240 milliseconds. The gap has gone from 6 times to 14 times in a single step. Concurrency to 200. Atomic update, 2,300 requests per second, essentially flat from the 100-worker run. Postgres is absorbing the extra load without breaking a sweat. Advisory lock, 94 requests per second, P99 latency 610 milliseconds, and the error count starts climbing off 0 for the first time. I pulled up pg_stat_activity mid-run on the advisory lock version and watched it happen live. Dozens of sessions sitting in wait_event equals advisory lock, all queued behind the exact same lock key, because every single one of these workers is checking out the same product. You can watch the queue grow in real time, 1 row per waiting worker. Concurrency to 500, the number from the cold open. Atomic update holds at 2,300 requests per second, P99 latency 40 milliseconds, barely different from the 200-worker run, like the extra load barely registered. Advisory lock, 61 requests per second. P99 latency, 2.9 seconds. 11 requests outright timed out and came back with nothing at all. Same correctness guarantee both fixes started with. Same overselling bug both of them genuinely fixed. 38 times the throughput difference by the end. And it isn't a rounding error. It's the difference between a fix that runs a flash sale and one that falls over during it. Here's the part that actually matters. Because atomic update wins isn't the lesson. The lesson is why it wins and where that stops being true. PG_advisory_act_lock takes an integer key, and every transaction requesting that same key gets serialized behind whichever one got there first for the entire transaction, not just the write. Check the stock, decide, update, commit. All of it happens one worker at a time, no matter how many other workers are waiting in line. 500 concurrent checkouts on one product means 499 of them are standing in a hallway waiting for a single door, and the line only gets longer as concurrency climbs, because the lock is held for the whole round trip, not just the write. The atomic update never takes an application-level lock at all. It hands the conflict to Postgres' own row-level machinery at the instant of the actual write for the shortest possible window, not the whole check-then-decide sequence, just the one row for microseconds. That's the entire 38 times gap. One fix serializes an entire transaction's worth of application logic behind a single named lock. The other serializes nothing except the individual row write Postgres was always going to have to order anyway. But, and this is the part that just use atomic updates everywhere, crowd skips. The atomic update only works because the whole invariant collapsed into one row and one where clause. The moment your rule spans two rows, two tables, or two separate statements, that trick stops applying. Reserve the seat, and write the booking record, and decrement a shared coupon count, all as one all-or-nothing unit. There is no single update that expresses all three at once. You need something that holds a critical section open across multiple statements until every one of them succeeds, or none do. That's exactly the job an advisory lock, or select, for update, is built for, and the 38 times cost we just measured is the price of a guarantee the atomic update literally cannot make. Notice, too, that the lock's cost is not fixed. It's proportional to how many transactions are fighting over the same key at once. Spread that same 500 requests across 50 different products instead of one, and the advisory lock barely slows down at all, because now each lock key only ever has 10 contenders, not 500. The bottleneck was never the lock itself. It was 500 workers all wanting the exact same door at the exact same second. So here's the actual rule, and it is not always use atomic updates, even though today's numbers make that tempting. If your invariant fits inside one row and one where clause, a stock count, a rate limiter, a single Boolean flag, the atomic conditional update wins outright. Identical correctness, dramatically higher throughput, and there's no lock object to create, name, or ever accidentally leave held. Reach for PG_advisory_act_lock, or select. For update, only when the invariant genuinely spans multiple statements or multiple tables, and the whole sequence has to succeed or fail together. And go into that choice accepting your trading throughput for a broader guarantee on purpose, not discovering the trade after your load test explodes in production. And before you reach for either one, if the actual shape of your problem is just don't let two inserts collide, a unique constraint plus a retry on conflict beats both of these. No lock at all, no dial to turn, no 38 times cliff waiting for Black Friday to find it. Passing the test suite told us both fixes were correct. It never once told us which one survives contact with 500 real users. Correct was always the floor. This is what the fight above it actually looks like, in milliseconds. Would you ship the advisory lock anyway for the wider safety margin? Or is 38 times the throughput worth the smaller blast radius the atomic update gives up? Tell me which one below. If this made a database lock click for the first time, hit like and subscribe. It's genuinely what lets me keep building these out loud. Next up, I'm taking the losing autocomplete agent from 2 videos back and testing whether it can even explain why its own fix was wrong, once cursors and Claude Code's working fixes are sitting right next to it on screen. See you there.